Hey everyone, it's Ken. In this video I want to show you how to prove the fundamental theorem of calculus part 2. Actually, I'll say a little bit about that. In many calculus books it's sort of broken up to part 1 and part 2, whereas I think most mathematicians just sort of think of it as like the fundamental theorem of calculus. For me, the way I like to present it, I like to do the second part first, and so that's what I'm going to show you. And intuitively, what this theorem says is that if you take any continuous function, then that function will have an antiderivative, and I can show you how to construct that antiderivative. And in fact, there are functions that are not continuous that do have antiderivatives. The fundamental theorem of calculus doesn't say that can't be the case, but just what it does say is that if you are a continuous function, then we can guarantee you that an antiderivative will exist. So let's get into it. So here's the statement. So fundamental theorem of calculus part 2. So what I'm going to do is the following thing. So say that we're given a function y equals f of x, and known to us to be a continuous function on some interval from a to b. So I'm going to define a new function that's going to become the antiderivative of little f. And this new function, the variable is actually going to go up here in the upper limit of the definite integral. So what I'm going to do is I'm going to integrate this function, little f, call it f of t, all the way from a to x. And dt. And the picture of this is, say you've got some function f defined on the interval from a to b. It looks like that, nice continuous function. And this function capital F, you put in an input x, and the output of capital F is going to be the signed area under the curve starting at a and ending over here at x. So certainly capital F of a is going to be 0, because that would just be the integral from a to a. And the fundamental theorem of calculus says that the derivative of this capital F is actually equal to little f. So it says that capital F prime is little f, or to write it another way is to say that in Leibniz notation, the derivative with respect to x of this integral a to x, f of t dt. This is going to be equal to little f of x. And I'll show you lots of examples later, but in this video I want to give you a proof. And really, as you've seen in many of our proofs, our recourse, what we can do is just use the definition and try to follow our nose, go from step by step, and see if we can get at the conclusion. And this proof is really fun. It uses a lot of information that we've learned throughout the course. So what I'm going to go is straight back to the definition. I'm going to use the limit as h goes to 0. And I'm going to look at f of x plus h. So that's a to x plus h minus f of x, right? And then everything divided by h. So I have to calculate this limit and show that it's equal to little f of x. And the first thing I'm going to do is, in a previous video, remember we said that when you've got two adjacent intervals, like from a to x and then from x to x plus h, then what you can do is you can say that this integral from a to x plus h is actually equal to the integral from a to x plus the integral from x to h. And let's go ahead and kind of, write that out, or I'll just leave that as an explanation in words. So think of this one. This one is equal to integral from a to x plus integral from x to to h. And then that's going to cancel with this integral from a to x. What you're going to be left with is just the integral from x to x plus h of f of t dt all over h. And as I mentioned in that previous video where I explained how you could break up the integral over adjacent intervals, it doesn't really matter whether h is positive or negative. It doesn't matter whether x was actually in between the interval from a to x plus h or not. You can always break that up. So if h is positive, then this will be bigger than x. If h is negative, then this will be sort of like the situation where you've got going from b to a instead of a to b. But either way, that's still okay. That's still part of the definition of the integral, and this will be true. And of course, I'm taking a limit, so I should be careful and not be too glib. Sneak in that limit. So h goes to 0. And so what am I really looking at here in this picture? So what I'm going to say, let's go over here. And so where's h in this picture? So h is like some small step size, and then you've got x plus h over here, right? And if I look at this integral, what is it really? It's the area under the curve from x to x plus h. And so and h is getting smaller and smaller and smaller. And I've drawn h so that you can see it here, but you think of it as being like a super tiny thing. And the thing about continuous functions is that the characterizing property of them is that the y values of your function can't change too much if your x values don't change too much. So as long as the distance between x and x plus h is very, very, very small, going to 0, then it's going to be true that on a small enough scale, f of t is not going to change very much from its value at f of x. So, and I'm sort of hand-waving this a little bit, but that's because we didn't use if I had the precise definition of the limit, I could tell you this precisely. But what I want you to think is that when h is really small, it's really okay. Since we're taking a limit, to replace this integral with what it's approximately equal to. So instead of just looking at f of t, I can replace f of t with its value, f of x. So instead of f of t from x to x plus h, if h is small, the value won't change very much, and then this straight line will be a good approximation. So I can just look at that constant, f of x, dt, all over h. And so why do you care about that? You're replacing the actual area under the curve with the area of this rectangle. And the approximation is not so good in that picture, but that's just because I drew it, big enough so you could see it. And when you take the limit, it'll pass from being an approximation to being a real equal sign because of the fact that function f was continuous. And so this integral of a constant we learned in a previous video. Integral of a constant is nothing but, the area of the rectangle, so it's going to be base times height. The base has length h and height f of x. So this is going to be limit as h goes to 0 of h times f of x over h. And I said the length of the base was h, but because that's the way I drew it in the picture. But if h happened to be negative, then your rectangle would be like over there. And that's still no problem. They're both negative and they both cancel out either way. So then you're just left with the limit as h goes to 0 of f of x, which is, of course, f of x. And that's how you show the fundamental theorem of calculus, part 2. And if I so this side has to be equal to that. And I'll go ahead and rewrite it since it's so important. The derivative with respect to x of this definite integral going from a to x, f of t dt, that's equal to f of x. So this always works whenever your original function, f of t, is a continuous function on the interval from a to b, then this function will be differentiable. This will be its derivative, and then that's called the fundamental theorem of calculus, part 2.